This is 11.4, which is going to be introducing 6 new differentiation rules. So what I have done is I have put up all your old ones that we learned before this chapter 11. So for example, something like the product rule or the quotient rule. And what I've done is I've combined that also with our new ones for this chapter, which are introducing how to differentiate inverse trigonometric functions. The ones that I did not include are those 6 new ones that we learned in 11.2, which was dealing with how do you differentiate just regular trig functions. So those ones I am expecting you to memorize, and just to warn you, colleges would expect you to memorize all of these, I believe. So just keep that in mind as you're seeing these patterns and noticing kind of ways of how you could memorize them. So what I'm going to break down one of these. We're just going to look at how you would be differentiating arctangent, for example. So understand that I am looking at these in terms of what if you were looking at a composition function. So something, for example, like arctangent of, let's say, x squared. Okay, so here we have an example of a composition function. I hope you're really starting to see functions as composition functions when you have this inner and this outer function going on. So if I wanted to derive this, just breaking this down and how you use this, if you were just looking at arctangent alone, this is the outer function. How you derive that outer piece, arctangent would require you to take 1 over and then 1 plus, and then whatever you're taking the arctangent of, or the inverse tangent of. So we're going to take x squared, and then you would square that. So, square that. So then, this is where that chain rule comes in. Because it's not just arctangent of x, what we are going to be doing is having to look at this as another function and deriving that. So on the outside I am going to be multiplying 2x, so the inner function's derivative. So that's how we work this. Here's the outer function being derived, leaving the inner alone. Okay, there's the inner function right there. But then you have to go back and derive the inner. So the chain rule, along with this new rule of how do you derive the inverse tangent. So if you want to, you can use this formula to the fullest. This is just kind of putting it all together. Here, I mean, when you're looking at this, you're deriving arctangent of this inner function with respect to x. So I'm going to go ahead and let this inner function be x squared. And then if I wanted to, I could say, well, the derivative u with respect to x, which is also notated as u prime, is equal to 2x. So therefore, you can just use this. This is kind of it in pieces. This is it all put together when we're trying to derive inverse tangent. So then you can just kind of fill this in appropriately. We have 2x over 1 plus u squared, so x to the 4th. Okay. So this I could simplify as well, put that 2x on the top. No, we obviously get the same answer. This just leads me to address that if you had the inverse tangent of just x, what you would have to do then is just go ahead and derive this this function, which is going to be 1 over, and then using it, it'd be 1 plus, and then whatever you're taking inverse tangent of is going to be squared. So that right there, you don't need to multiply it by the inner function's derivative because there is technically no inner function just derivative, it's just x. So I mean, if you did that, it would be multiplied by 1. So I guess if you're looking at all of these, the du dx would be taken out of all of these if we were just taking the derivative of an inverse function with respect to x. Whoops. Alright, so I'm going to go ahead and work through number 13 with you. 13 looks like this. So I'm going to be trying to find the derivative of this given function. So I'm going to be finding h prime of t. Here I'm going to have to recognize that there's an obvious composition function going on where my u, this is my inner function. T is going through arc cosine, and then whatever that is, it's going to go through sine. So when I am going to be assigning this u, I'm going to be looking at this as my inner function. Arc cosine or inverse cosine is the inner function. And then I'm going to have to recognize, because that chain rule, originally what we're going to do is just derive this outer function and leave this inner alone. So I'm going to do that. I'm going to derive this outer function. It's going to be, when we derive sine, here, let me write out this. Okay, so here we're going to leave that alone at first, just ignore it, but we do have to derive this outer function. When we derive sine, that's one of those that I'm going to have you memorize, so hopefully you remember that as cosine of u. And then you have to tag on what is the derivative of that u. So here I'm going to do a little work off to the side. Arc cosine of t, that's when you would use your properties here. It's just going to be this -1 over the square root of 1 minus, and then whatever you're taking the inverse cosine of, it's t here, and we are deriving with respect to t. Notice how we have this, we're deriving h with respect to t, so du dt is equal to u prime. So here it's just going to be -1 over the square root of 1 minus what we're taking the arc cosine of, so squared. Okay, so this is what's going to have to be multiplied on, so I am just going to write this as u prime for now, and then I will fill this in. So we have cosine of that inner function left completely and entirely alone, times, and then here is where we're going to have to multiply by that u prime. So the best way to do this is going to be cosine arc cosine of t, and then negated, because that's all going to be multiplied by -1, all over the square root of 1 minus t squared. Now here is the thing. We are going to simplify this, or be able to simplify this even a little bit further, because what I have done is I'm taking the cosine of arc cosine. So remember, these are inverse functions of each other. There's something that they undo each other. So what we're going to be able to say then is this is going to be negative, and then since these are going to undo each other, we're going to get t, whatever that input was, and then all over 1 minus t squared. So there we have it. That's the answer to number 13. I'm also going to look at 26, and what 26 does is it gives you a formula basically that you have to use. And this formula is what we call a linear approximation, and this is not part of your homework. I asked you to do number 25 as part of your homework, but what you're doing is a linear approximation of a given function, and what they gave us was f of x is equal to arctan of x, and they're saying that you're going to be looking at the linear approximation at a equals 1. So we're going to look at that real quick. So I'm going to go ahead and say, well, this is going to be arctan of a, so here I have it right there, plus, and then I'm going to need the derivative. I'm going to have to derive this function with respect to a. So what is f prime of a? So the derivative of this function with respect to a of arctangent of a, and then all of that times x minus a. So the first thing that you're probably going to want to do before you even start plugging all of this in is you're going to want to derive this piece right here. So arctangent of a plus, and then this is where we're going to be using our formula. So I'm going to need 1 over 1 plus a squared times, and then this one, we're deriving a with respect to a, that's just going to be times 1. So this is all going to be times, and then x minus a. So now here is when I'm going to actually plug in my a. So I have arctangent of 1 plus 1 over 1 plus 1 squared times x minus 1. Okay, so the first thing that I did was I went ahead and just used that formula that they gave us for this linear approximation, and I used it completely, just filling in I mean basically using the function and filling in a where I needed it for this particular formula. Then what I went ahead and did was I derived the piece that I needed to, and then what I had left was some sort of formula where I could go ahead now and plug in my a's. So now that the a's are all plugged in, what I will say is these are simplifiable, if that were a word, I think it is. But I'm going to go ahead and solve for what is arc tangent of 1. Remember, tangent is only looking at this side, or I'm sorry, inverse tangent has a restricted domain and range, and it's on this side of our unit circle. So it's only this piece right here, pi over 4, that will actually fulfill this requirement. We're asking ourselves what angle is equal to what when you take the tangent of it is 1. So that's what I just solved for, pi over 4. Plus, this will simplify to be 1/2 over x minus 1. So now when we simplify it even more, the linear approximation at this particular point, a equals 1, is going to be 1/2 x minus 1/2, and then plus pi over 4. Okay, so right here, I'm going to say that this is fine to leave it in this form, but what I did do was expand it out here, and then so I had 1/2 x minus 1/2 plus pi over 4, and I did simplify it here to be 1/2 x plus and then approximately 0.285 when I simplified this piece. So what this is actually meaning to us is when you're saying a linear approximation, your calculator does have the capability in the programming to do that. So this is what a potential program in your calculator would look like if you ever did want to program your calculator to find a linear approximation of a graph at a certain or particular point. Then you could use this formula right there to program into your calculator. So what it's doing is, or what you would be programming your calculator to do, if you look at this particular graph, I went to a random website and captured a screen where they had graphed the inverse tangent. And what I've done is I put that equation that we came up with, that linear approximation equation that we came up with using that formula, and I've drawn that blue line in. So remember, when you're looking at a linear equation, it's kind of hard when you have something so curvy as this to ever say that this would ever be a linear line. But if you had to draw a line to try to equalize all the points on one side and the other, what we've done is we've come up with that line. So here is that linear approximation that we have at that point 1, at a equals 1, and what it is doing is it's kind of dividing all of our points to be on one side of it and then the other side of it equally. So we came up with that, which is, neat. Applications for this, there is a lot of approximations that have to be done when you're looking at data. Linear, if you were a real analyst of this, you would probably say this was not, a linear line will not be the best approximation of this data if it were forming some sort of shape like that. So yeah, that's it. Okay, so I'm kind of going backwards, but I felt like I should do one more problem with you, but just because I haven't done very many with you. But what I'm hoping you're seeing is the objective truly of this chapter is to introduce these 6 new differentiation rules, but I hope you realize that you really haven't learned anything that new, because what we're still just working on is being comfortable with being presented with these formulas and just being able to use them. And eventually you're going to be tackling that step of memorizing these, but not for my class. What I just want you to be really comfortable is I can be presented with any formula and I can work that formula. Just like we worked with that linear approximation formula, you're able to, as complicated as it may look, you're just able to use it literally for what it is. So here I'm just going to do one more, like I said, just to kind of do it. So number 7 is this problem right here. I rewrote it as this. So you do have a composition function because I have 1/2 times x inside this thing right here. This 3 on the outside, that's just a scalar multiple. So I will be using the scalar multiple rule, which is right here. And I have 3 times the derivative because I am trying to derive as my instructions has told me to do. Okay.
So now what I need to recognize is, if you want to off to the side, I'm going to let u equal 1/2 x, and then I'm going to have du dx equal 1/2 then. So when I'm deriving this, I'm going to have that 3 on the outside, and then I'm going to derive this outer function. So I'm using my arc cosine, which is -1 over the square root of 1 minus, and then that inner function left alone, squared. Okay, but then I have to tag on what is the derivative of that, which I said is 1/2 over here. So just simplify this now. I'm going to get 3 times -1 times 1, which is -3 on the top, and then all over 2 times, and then the square root of 1 minus. I could go ahead and distribute that 2 to get 1/4 x to the second. Okay, so there we have it.